right? Okay, so last Wednesday, we proved the forward part of the theorem. So we proved that if a function is invertible, then it is bijective. Okay, and so today I would like to prove the reverse part. So we assume that f is bijective. All right, now to show f is invertible, we want to construct the inverse of f. Okay, so so we now construct a function g from b to a. Okay, so we want to construct a function in the following way. All right, now for sorry. Okay, so now for a y in B, there is an x in A, such that f of x equal to y, since f is onto. Okay. Because f is bijective means that it is injective as well as surjective. Surjective means onto, right? So so f is onto, so every element in the codomain is an image of an element in A, so that we can find an x such that f of x equal to y. Right now, if there is another x prime in A such that f of x prime in B is equal to B. So if there is another x prime in A such that f of x prime equal to y, then we must have x equal to x prime, since f is 1 to 1. Okay. All right, so this unique x will be assigned, right, as the value right, as the value of G at Y, i.e. X is assigned to be Y. And this assignment is unique because there's only one X satisfy this condition, right? Any questions? Okay. As we know, to construct a function, we have to establish the rule how to map each element in the domain to an element in the codomain. Okay, and the way for such an assignment is by the help of the function f itself. Okay, so in here is that for any element y in the B now is the domain of G, right? Domain of G. We know there is an X in A such that the value of f at X is equal to Y, right? So there is such an X. And we show that such an X is unique, no other choices, by the one-to-one property of f. Okay, so there's no other choices. So this unique X, right? There's only one and only one X satisfies this one. And so the assignment is that we let X to be G of Y. So any questions about this assignment? All right. So now, that G is well defined. Okay, G is well defined. So the next job is to show that G is the inverse of F. Okay. So now, for any X in A, we have, right? So we check the composite of G and F, okay, on the X, because this composition is a function from A to A, okay, from A to A. So we check an element X in A. And this one is G f of X. Okay. But okay. So now we let y equal to f of x. Right? So we let y equal to f of x. Then, by the construction of G, we have, x is equal to G of y. Because whenever we know y is equal to f of x, then we know G y is equal to x by the construction of G. All right, so that's, now we plug into here G circle f, x equal to G of f of x. And this is G of y, because y is said to be f of x. And then G of y is x for all in A, which implies that G circle F is the identity of A. Okay, so that is the first. Now, also for any y in B, okay, we have F circle G of y. Right, so this composition is a function from B to B. So this is F of, okay. Now we let X to be GY. And again, and by the construction of G, when X is GY, right, X can be assigned to Y because Y is equal to F of X. Thus, we have F circle G Y equal to F of G Y equal to G Y is set to be X. Once we set X to be that way, then F of X is equal to Y. Okay, so which shows that F circle G is equal to the identity function of B. Okay. So from this one and this one, we conclude that G is the inverse and F is invertible. Right, so this is the end of the proof. Questions? Now, they are infinitely many kind of functions from Rn to Rm. For example, right, you can define a function from Rn to Rm as like the first component is the sum of square of the vector in Rn, or you can just the product. Okay, and this is m dimensional. So Okay, so the component can be arbitrary. Okay. So there are infinite many kinds of functions that you can allow like okay. For example, you may encounter many of such functions in calculus. Okay. But in linear algebra, we are most interested in a special kind of functions. So the following kind of functions. From Rn to Rm. Okay? So we give a definition for this kind of functions we discussed in linear algebra. A function t from Rn to Rm is called a linear transformation from Rn to Rm if T map a linear combination of two vectors x and y in Rn. Okay, so x, y are vectors in Rn, and this is a linear combination of these two vectors. Then the image of this linear combination is equal to a linear combination of the image of x and y. Okay. So they preserve the form of linear combination. Okay. In here, we have a linear combination of x and y with coefficients alpha and beta there, respectively. And then the image, okay, in Rm takes the same formation of linear combination. It means that they keep the same corresponding coefficients alpha and beta, but the vector has been replaced by their images by t for x to tx, y to ty. Okay? Right? So this is really a special kind of function from Rn to Rm, a very special kind. And it preserves the linearity formulation. Okay, in here. Now, our job here is to characterize such kind of function. Okay. Now, the first characterization is here. A very convenient way to construct a linear transformation can be stated in this theorem. So let A be an M times N matrix. Over R. Okay. Define over R means that the entries of the matrix are real numbers. Okay, so that A is a real matrix. Now define a function t from Rn to Rm by the following formula: t on x. So x is so this one is m times 1 is equal to a multiplied with x. This is m times n, and this is n times 1. For all x in Rn. Right? So now take an m times n real matrix and construct a function in this way. So every vector x in Rn give us a vector in Rm by multiply x with the matrix A from the left. Okay. Now then T is a linear transformation. Okay. So this construction gives us linear transformations. So the proof is like this. So now for all x, y in Rn and alpha, beta are real, then t alpha x plus beta y. All right. Well, equal to a multiply alpha x plus beta y. Okay. By definition. And by the rule of matrix multiplication, we know this is like this one. And this is Tx plus beta Ty. And we have done. Okay, so it's quite simple to see that. So this is very convenient, right? To construct a linear transformation from Rn to Rm, you just use an m times n matrix. Oops. And the next discussion is that we will show this is basically the only way to establish a linear transformation from Rn to Im, basically. Okay? This is the only way. Okay, so, but before that, we introduce standard basis, standard unit vectors. So the vectors E1, 1, 0, 0, E2, 0, 1, 0, that En, 0, 1. Okay. In Rn are called standard unit vector in Rn. All right, so in Rn we have n standard unit vectors. So U1 is that the first component is 1, but the raised component are zeros. E2 is that the second component is 1, but the raised components are 0. Up to En, except the last component, which is 1, other components are zeros. All right, so they are called standard unit vectors. Now, any vector x, x1, x2, up to xn in Rn can be represented as here x1, x2 up to xn can be written in the following way. All right, so can be written as a linear combination of unstandard unit vectors. And the coefficients are just the components of the vector x. Okay, so you can see that we have this one. Okay, so now if T is a linear transformation, and U1, U2 up to UK in Rn, alpha 1 up to alpha k in R. Then the properties can be extended. So in the definition, we just require that for a linear combination of two vectors, the mapping of T will preserve the formation of the linear combination, like this one. But this can be extended to k vectors. All right, so let's see how. So U1, okay. Well, this one we can think about as this linear combination can be written as a linear combination of two vectors. Okay, so this is x, and this one is y, and this one is alpha, and this one is beta. Okay, just like here, alpha x plus beta y, right? So you can think about that. This is one of the vector here. So one is alpha, and this vector, this linear combination is a vector called x, and this is beta, this is y. So by our definition of linear combination, this is 1 T of alpha 1 U1 plus alpha 2 U2 plus plus alpha k minus 1 UK minus 1 plus alpha k T UK. And then 1 multiply with a vector is just the vector itself. Okay, so the transformation of this linear combination And this linear combination is the linear combination of k vectors. Okay, is equal to the transformation of the linear combination of the first k minus 1 terms plus alpha k multiplied with the transformation of uk. Okay, and so we can do it recursively. So work out this linear transformation, this mapping. Doing the same thing, we will see that this is alpha 1, u1 plus alpha 2, u2 plus plus alpha k minus 2, u k minus 2 plus t plus alpha k minus 1, t u k minus 1 plus alpha k, t u k. Okay? And do it the same way, the same thing again in here, in many times. So we will have alpha 1 u1 plus alpha 2 u2 plus alpha 3 t u3 plus plus alpha k t uk. And finally, this is alpha 1 t u1 plus alpha 2 t u2 plus plus alpha k t uk. Okay. So you can see that linear transformation preserve the format of linear combination in general, not only for two terms, can be in general for arbitrary many terms here. Okay, give you that. Questions? All right, so if not, okay, so if T is the linear transformation from Rn to Rm, then there exists, all right, so there exists an M times N matrix A such that the image of T at x is equal to A multiplied with x for all vector in Rn. So this theorem tells us that any linear transformation must be this way, that we can find an M times N matrix A, okay? And then the T of x is equal to A times x. So any linear transformation is the type of this one. All right? Now, so the proof is that to construct such a matrix A explicitly, all right, so we have to construct such a matrix A. Now, so for an x, so for a vector in Rn, okay, we know from our previous discussion here, we know that the vector x can be written as a linear combination of standard unit vectors. All right, so now when we look at the image of x by t, this is x1. And with the properties we just discussed here, the image of this linear combination, right, will preserve the formulation or the format of this linear combination with the same coefficient. Okay. All right, and we can put this linear combination into matrix multiplication. So this is TE1 as the first column, TE2 as the second column, etc. up to TEN as the nth column, multiply with. Okay? And then this is AX, where A is defined to be TE1, T. Okay, so this is an M times M matrix. And we have done. This is the end of proof. So we know how to construct the matrix A. The matrix A is formed by the image of the standard unit vectors by T. So that the first column of A is the image of E1 by T. The second column of A is the image of the E2 by T, etc. Okay, so that from the proof, we end up with the following theorem. So a linear transformation T from Rn to Rm is completely determined by the images of A on the standard unit vectors E1, E2 up to En in Rn. Right, just like here. Once we know the image of T on E1, E2, and En, once we know that, then we can construct a matrix A. And then T of x is equal to A multiplied x. Okay? So the proof is that this follows from the proof of the previous theorem. Okay. So do you have any questions up to now? All right, so up to this point, we know how to characterize an arbitrary linear transformation from Rn to Rm, right? Because that is directly related to an m times n matrix. So basically, an n times n matrix corresponding to a linear transformation. Okay, so they are one-to-one. Okay, they have a unique correspondence over there. All right, so at this moment, then you can think about that. If you know matrix well, then you should know linear transformation very well. Up to now, even though I just introduced the concept of linear transformation today, but it seems like they have become your good friends already. Yeah. Okay, so let's take a break right now. Okay, an announcement. Starting from next week, all students are required to take the quiz in person. So you have to come to this building to take quiz. And we will provide an overflow room in room 202. This is room 216, right? But we will provide room 202 as the overflow room, okay? Because we still have a limited capacity in this classroom, even though has been increased from next week, all right? So there is no more remote taking quiz, okay? No, come here. All the students in air, you should know that. So you have to come, right? Every Wednesday at least. And it could be hard for you to sit in your dormitory and look the direct broadcast, and then maybe you fly to the building to take quiz in another room. You want to do that, then up to you, okay? Because time is for you yourself. You want to waste your time, you just go ahead. Because the time start with the 11:20, right? So I recommend you to come earlier to bring your notebook to the overflow room to look the direct broadcast. And then take the quiz later on. All right, now, by definition, a linear transformation is a function, right? And we have mentioned about bijective functions or injective functions, surjective functions. So we would like to categorize under what condition a linear transformation is an injective function. All right. Also, we want to categorize under what conditions a linear transformation is surjective. Okay, and you will see that these conditions are concepts you already learned before. Okay, so here is the first one. All right, so a linear transformation T from Rn to Rm, which is represented by a matrix A, like this way. And we already proved that every linear transformation can be represented in this way. All right, for some M times M matrix A. All right, so such a linear transformation is surjective. Okay, i.e. onto if and only if the column space of A is equal to Rm. Okay, so now we have a sufficient and necessary condition. for a linear transformation to be surjective. That is that the representative matrix A should have a column space which is equal to Rm. Okay. So we first prove the forward part. Now since T is surjective, okay, for any y in Rm, there exists an x in Rn such that y is equal to, all right, so that there exists an x such as y is equal to tx. And so A1, A2, An, x1, x2. Okay, so A1, A2, An, they are all columns of matrix A. Okay, well, maybe maybe too fast. This is Ax, right? And this is equal to that. So this is x1, A1 plus x2, xn. Okay? And this is in the column space of A. Because it's a linear combination of the columns of A. Okay? Okay, so this is columns of A there. So any y, any vector in Rm in the codomain, any vector in the codomain, is also in the column space of A. So this shows that Rm is contained in the column space of A. But column space of A must be a subset of Rm. So the column space of A is equal to Rm. Okay? So this is the end of the forward part. Backward part. Now since Rm is equal to the column space of A, for any y in Rm, right? Rm is the codomain of the linear transformation T, right? So for any vector in the codomain, and because Rm is equal to the column space of A, so there exists alpha 1, alpha 2, up to alpha n. There is a typo, okay? Because I type a singular form, but this is incorrect. So please remove it, okay? So there exists in R such that Y, because Y is in the column space of A, so Y should be a linear combination of the columns of A. Okay? And then this linear combination can be written as symmetrical multiplication. Okay? And now, because of this representation, this is T of alpha 1, alpha 2. So that this is in the range of T. Okay? So it's in the range of T. To TR. TR, because Rn is the domain, so T over Rn is the range. Okay? So this is the range. Okay. Okay, so every y in the codomain. So this is the Rn, the codomain of T, all right? So Rm is the codomain of T, and Trn is the range of T. So every vector in the codomain of T is in the range of T. So this shows that the codomain is a subset of the range of T. But the range of T must be a subset of the codomain. Okay, this is the general property of any function. Okay, for any function, this is general. Okay, so that the codomain is equal to the range, and T is onto. End of the proof. Okay. All right. So we find a necessary and a sufficient and necessary condition for a linear transformation to be onto. And this condition is that the column space of the corresponding matrix A should be equal to the codomain Rm. Okay. Before we introduce a condition for a linear transformation to be one-to-one, we need a concept called the kernel of a linear transformation. The kernel of a linear transformation T from Rn to Rm is the set of all vectors in the domain Rn such that the image is the zero vector in the codomain. So that we denote it as the kernel of T it's all the another typo. Okay. I type R to M, but it's N is not M, okay? So maybe it's N, okay. So for all vectors in the domain, okay, of T, such that Tx equal to 0. So kernel of T is a subset of the domain, okay? So kernel should be a subset of the domain. On the other hand, the range of T is a subset of the codomain, okay? So you have to, so I'm so sorry for my typos here. Okay, now I introduce a supplementary theorem, 2.3.b. So later, a linear transformation T from Rn to Rm be represented by an M times N matrix A as Tx equal to A times X for all vectors in Rn. Then the kernel of this linear transformation is equal to the kernel of A. Okay. And the proof is quite trivial. A vector X is in the kernel of the linear transformation. By its definition is that T on X is equal to the 0 vector. Okay? But this is saying that AX is equal to 0 because Tx is equal to AX. Okay? And this is showing that X is in the kernel of A. Okay? Okay, so X, so implied as X is in the kernel of A. Okay, so a vector in the kernel of T, if and only if a vector is in the kernel of A, so the conclusion is that kernel of T is equal to kernel of A. Now we have a simple lemma for any linear transformation T from Rn to Rm. We have that the image of t at 0 is 0. Okay. And the proof also quite simple. For any x in the domain of t, we have 0 is equal to x minus x. And then t0 is equal to t on the difference. Okay. So x minus x is a special type of linear combination. So this is equal to tx minus tx. And of course, this is 0. Okay. So this is bilinearity of the linear transformation, right? All right, so now we can state a theorem. All right, so a linear transformation T from Rn to Rm is injective. Sorry, another typo. Okay, I write infective. Actually, it's injective. I'm sorry. If and only if. So. Okay. If and only if the kernel of T consists only 0 vector. Okay, means that it says that the kernel of T is trivial. Okay, it's called trivial because it is just the set of the 0 vector. Proof. All right, the forward direction. So we let x is in the kernel of T, i.e. T on x is equal to the 0 vector. Okay? Now we know T0 is 0, right? By lemma 2.3.b. We know that T0 is T0. So x and 0 has the same value, 0, right? Tx is 0. We have Tx is equal to T0. And then x must be equal to 0 since T is injective. Okay, T is 1 to 1. Okay, so if they have the same value, then these two elements, these two vectors must be the same. So x is equal to 0. So any vector in the kernel is actually 0 vector. Okay, therefore the kernel of T consists only 0 vectors. Okay, so we have done the forward part. How about the backward part? So we have to prove that if the kernel of T is 0, then T is injective. Okay, so we assume that Tx equal to Tx prime. Okay, for x prime in the domain. Okay, so suppose we have two vectors in the domain and they have the same value. then we have to prove that x equal to x prime. Okay? Then we have that 0 vector is equal to tx minus tx minus tx prime, because they have the same image, right? So the difference is 0. And the bilinearity of linear transformation, okay? This difference is the t of x minus x prime. Okay? So this implies that x minus x prime is in kernel of t, because the image of the difference is 0. So the difference is in the kernel of t. But the kernel of t is equal to this set. So this implies that x minus x prime must be equal to 0, and this implies that x equal to x prime. All right? So t is 1 to 1. End of the proof. Okay, now the last concept is about we know the composition of two functions. So now we want to characterize the composition of two linear transformations. So it's a combination of two theorems in the textbook. Now, if T is a linear transformation from Rn to Rm, and the X is another linear transformation from Rm to Rk, right? So both of them are linear and such that their metric representations like this one, such that Tx is equal to Ax for all x in Rn, and x y equal to b y for all y in Rm. Okay, so we have that. Of course, that A matrix is M times M matrix, and the B matrix is K times M matrix. Okay, so we have that. Now, then, the composition of these two linear transformations is also a linear transformation. Okay, and its metric representation okay, its metric representation is the product of the two matrices B and A. Okay. Okay, so it's B multiplied with A. Okay, so this is K times M, and this one is M times N. So together is K times N matrix. Okay. So now, for all u v in Rn, alpha beta in R. So now we have to prove that the composite of these two linear transformations is also a linear transformation. So we have to prove its linearity. So that we check that. Okay. Now this composite function, all right, and we take its images at this linear combination. All right, and by definition, so this is okay. Is that? So we take the image of this linear combination on T, and then by X. But T is linear, right? It's a linear combination. So this is alpha Tu plus beta Tv. Okay? Okay, so now here again, this is a linear combination of Tu and Tv. And because X is a linear combination, so by the linearity of X, so we have alpha S Tu plus beta S Tv. Okay? And what is that? This is X circle T on V plus beta S circle T on V. Okay, so again, we preserve the format of linear combination. Okay, so that this shows that it's a linear transformation. Right? So from Rn to Rk. Now, how about its metric representation? All right, so also we have, okay, the X circle T, X, okay, it's X, T, X, okay, and which is X, but T of X is AX, okay, AX. By this formula, T of X is A times A multiplied with X. And this vector, after this mapping, is B of A X here. Okay, so we just apply the matrix representation here. And because matrix multiplication is associative, right? So we can multiply B and A first and then X. Okay, so you can see that we establish this. Okay, so we have that. And then we're done. Any questions? Okay, so the third section of chapter 2 give us a tour on the general concept of functions. So we review the general concept of functions. Okay, we talk about some properties about the invertibility of a function. And before that, we characterize what kind of function well, can be called as one-to-one. What kind of function can be called as onto, right? And we also review the concept of composition of two functions. Now, all of these concepts apply to linear transformations because linear transformation is a very special kind of function from Rn to Rm. Okay, special kind of function because we have linearity there. Okay, and so with the linearity of linear transformation, we are able to characterize what kind of linear transformation to be one-to-one, what kind of linear transformation to be onto. Okay, and we also characterize that any linear transformation is associated with a matrix. Okay, and such a matrix can be used to construct a linear transformation. Okay, so that's everything about that. Okay, and so at this moment, we can say that we have some information or knowledge about the vectors in Euclidean space, Rn, right? So we are familiar with vectors in Euclidean spaces, and we know how to do the manipulation, especially linear manipulation of vectors in the Euclidean space. All right, and also we just consider the linear transformation from n-dimensional Euclidean space to m-dimensional Euclidean space. Okay, so we have a lot of experience. And this experience are so valuable that we will have a very huge extension to other domain of subject in mathematics, engineering, economics, finance, life science, a lot of things, science and technology. So we are going to consider general vector space. All right, so I want to repeat a paragraph in my lecture notes. So experience on the linear manipulation of vectors in N. We are interested in studying vectors of types other than column vectors. In Rn, and which allow similar linear manipulation. Sorry, maybe I have different kind of manipulations there. Okay, so we will generalize the concept of vectors. Okay, you will see that a lot of objects, okay, can be regarded as vectors. Okay. Right. So that, but to introduce the concept of a general vector space, we need a Cartesian product. All right, so Cartesian the Cartesian product denoted as A times B, A cross B, of two sets, A and B, is the set of all ordered pair, little a, little b, with little a is in big A, and the little b is in big B. All right? So the Cartesian product of two sets, A and B, just the set of all ordered pairs. Okay, so A cross B is pairs like this one, and the first component is from set A, and the second component is from set B. Okay. All right, so examples. The two-dimensional Euclidean space can be regarded as the Cartesian product of R with itself. Okay, so that ordered pair. Okay. In general, the n-dimensional Euclidean vector space Rn can be regarded as R, Cartesian product R, for n times, which is regarded as ordered sequence. Okay, and the component are in R. Right, so this is called Cartesian product. Okay. I have 5 minutes left. A vector space over R, all right? Okay. Currently, we can omit over R, okay? Because we talk about real vectors, real matrix, real everything is real, okay? But later on, we will see that we can over complex numbers, complex matrix, lot of things. All right, so I just say that over R. All right, so a vector space basically is a set. All right, so it's a set of elements, just an arbitrary set, and this element will be called vectors. So it's just a set of elements together with, together with two algebraic operations. One is called vector addition. Okay, all right. So it's an operation called plus addition. Okay, or plus addition, and the addition actually is a mapping from the Cartesian product of the set V. A set V. I forgot to put V. Okay. So it's a vector addition. Right? So every pair, Cartesian product by our definition is the set of all ordered pair. Okay, so it's a pair. And the first component is from the first set, second component is from the second set. So for this set, it will go to what? Go to, so the image is U plus V. Okay, so we have to define so-called vector addition, right? And it's sometimes called the sum of U and V. All right? So first of all, we have to define an algebraic operation called vector addition. Okay? So for each pairs U and V, we add them together. We should find a rule to add them together, and so that this sum must be a vector, a member in the set V. Okay, this is the first thing. The second thing is called the scalar multiplication. And usually it's a blank, okay? It's usually a blank. So it's from the Cartesian product of R and V to V, which says that with a scalar alpha and a vector in V, right? The blank, this one is alpha U. Okay? So it's the scaled vector of U by scalar alpha. So we should find a way to scale up or scale down, okay, a vector U. Okay, and so I put just a blank, okay, to denote it's a scalar multiplication. All right, so it consists of at least three things. First, very simple, a set only, just any set. And then you should have some means to define the so-called addition of two vectors, such that the sum is a vector in V. Okay. And also somehow you have to able to define the so-called scalar multiplication, so that you can scale any vectors in V to obtain a new vector in V. You call alpha U. All right? But not arbitrary vector addition and scalar multiplication will work. There are some rules to be followed. So such that the following 7 axioms are fulfilled. Okay? And of course, I haven't enough time to state all the 7 axioms right now. Okay, so I will state that next week. But the important thing I have to say is that to extend our experience of linear manipulation of column vectors in Rn. All right, we want to expand this experience to some object. There are some preliminary work to do. Okay? If you think about that, all the vectors in n-dimensional Euclidean space is just our Earth. Okay, we are very happy. We know everything about the Earth, all the things function. But we would like to, our lifestyle, our manner to Mars or forever. Maybe Mars is not a good choice, right? Because we know the condition is not very good for us, for human beings, right? Maybe in some planets in the universe far away from us. So that we have to check, we have to send the explorer, okay, to see some essential condition. And this condition should be analyzed first to answer several questions before we send the human being to that planet. Okay? So there are settings that some requirements for human being can colonize in another planet far away from Earth. All right, so this is just a similar situation that we want to extend our experience in Euclidean vector space. Go to so-called general vector space, all right, and do the similar linear manipulation and solve a lot of related questions and problems. Then we will ask that such an object should form a system. And this system should have some essential property itself. Otherwise, we can't extend our experience to that system. Okay? So in next week, we will take some time to examine some necessary condition we call axioms. Okay, axioms is something that we can't prove. Right? It's there, already there. Okay, so we have to justify whether these 7 axioms exist for the new system we would like to investigate. And we would like to extend our experience in the Euclidean vector space. Okay? All right, and it will surprise you that there are a lot of different systems, right? With the required axiom, we require the essential structures for us to extend our experience in the Euclidean vector space. And that's why linear algebra is so important, so basic in science and technology, because that you can extend your experience unbounded, all right, in any way. Okay? Okay, so I'll stop here, and hope you have a happy double 10th holiday. Don't forget exercise. And also, I remind you, even in the holiday, our TA is very diligent for you, because we will have the recitation session again on Monday evening, okay? So you are welcome to attend the live broadcast, okay? Okay, so see you next week.